NENOMATICA, where mathematics meets YouTube excellence. Now we will display the statement of the theorem on screen in orange and bold. Step 1. Decompose each real number into its integer part and fractional part. We'll show the rule in a tip box. Then we will write the decompositions for x and y. Quick challenge. If x equals 2.7, what are the floor of x and the fractional part of x? Step 2. Add the two expressions. We will use the addition property. Now we add the equations for x and y. Notice we will highlight x plus y in orange to emphasize the change from the previous step. Step 3. Apply the floor function to both sides. We use the property that if two expressions are equal, then their floors are equal. Now take floors. We'll highlight the floor of x plus y in orange. Step 4. Pull the integer parts outside the floor. If n is an integer, then the floor of n plus a equals n plus the floor of a. Here, both floor of x and floor of y are integers, so they come out. We will highlight their sum in orange. Step 5. Analyze the range of fractional parts. The fractional part of any real number is at least 0 and less than 1. Therefore, the sum of the fractional parts lies between 0 and 2. This implies the floor of their sum is either 0 or 1. Step 6. Conclude the inequality. If a equals b plus c, with c non-negative, then a is at least b. Since the floor of the fractional sum is 0 or 1, we have the floor of x plus y is at least the sum of the floors of x and y. This completes the proof. Let us verify with two quick numerical examples. In the first example, 2.3 plus 1.8 is 4.1, whose floor is 4, which is greater than or equal to 2 plus 1. In the second example, 0.5 plus 0.5 equals 1, whose floor is 1, which is greater than or equal to 0 plus 0. In this example, we will prove a classic integrality result using Legendre's formula. First, we state the problem clearly on screen. Step 1. We define the numerator and denominator of the fraction and set up our divisibility goal. Then we write capital D equals m factorial times n factorial times quantity m plus n factorial, and capital N equals quantity 2m factorial times quantity 2n factorial. Quick challenge. What must be true for n divided by d to be an integer? Step 2. We will compare prime exponents using Legendre's formula. For any prime p, let lowercase a be the exponent of p in d, and lowercase b be the exponent of p in n. Then a equals the sum over I of floor of m over p to the I, plus floor of n over p to the I, plus floor of m plus n over p to the I, and b equals the sum over I of floor of 2m over p to the I, plus floor of 2n over p to the I. Our goal is to show a is less than or equal to b. Step 3. We reduce the comparison to a termwise inequality with substitutions. Let capital R equal m over p to the I and capital S equal n over p to the I. It suffices to prove the inequality. Floor R plus floor S plus floor of R plus S is less than or equal to floor of 2 R plus floor of 2S for each I. Because adding an integer to R or S increases both sides equally, we may assume the fractional parts only. Step 4. Under 0 to 1 bounds. Floor of R equals 0 and floor of S equals 0. So inequality I becomes floor of R plus S is less than or equal to floor of 2 R plus floor of 2S. Consider two cases. Case 1, R plus S less than 1. Then floor of R plus S equals 0. And the right-hand side is non-negative, so it holds. Case 2, R plus S at least 1 and less than 2. Then floor of R plus S equals 1. Since R and S are both less than 1, at least one of them is at least 0.5. So either floor of 2R or floor of 2S is at least 1, and the inequality holds. Conclusion. Since for every prime p, the exponent in the numerator is at least the exponent in the denominator divides the numerator. Therefore, the expression is always an integer for all non-negative m and n. Welcome! In this video, we will prove an important property of the floor function, often called the rule of brackets for division by a natural number. We'll proceed step by step, following the standard inequality method based on the definition of the floor function. First, let's display the example and the statement we want to prove. As a useful reminder, if x is greater than or equal to some integer, n, then the floor of x is also greater than or equal to n, and conversely. This is sometimes used as a note, but our main proof will rely directly on the floor definition inequalities. Step 1. We start by letting k be the floor of x over n. By the definition of the floor function, k is the greatest integer less than or equal to x over n, which gives the double inequality k, less than or equal to x over n, and strictly less than k plus 1. Step 2. Since n is a natural number, it is positive. We can multiply the entire inequality by n without changing the direction of the inequality signs. This clears the denominator. Step 3. Now, we use the fact that the floor of x is the greatest integer less than or equal to x. From kn less than or equal to x less than k plus 1 times n, it follows that kn is less than or equal to floor of x, and floor of x is strictly less than k plus 1 times n. This is an integer-bound property. Step 4. Divide the entire inequality by n, which is positive, so the inequality directions stay the same. This normalizes the expression and introduces floor of x over n. Step 5. Now we apply the floor definition in reverse. If k is less than or equal to a real number, and it is strictly less than k plus 1, then the floor of that real number is k. Applying this to floor of x over 1, then the floor of that real number is k. Applying this to floor of x over n gives the floor of x over n equals k. Step 6. We started with k equal to the floor of x over n. We just showed the floor of x over n also equals k. Therefore, the two floor expressions are equal. Let's display the example and the target expression. Rule we will use: for any real x and natural n, the floor of x over n equals the floor of x over n, provided n is a positive integer. Now step 1. Apply the rule by taking the floor of the numerator first. Next, estimate the square root of 130. Since 11 squared is 121 and 12 squared is 144, the square root of 130 lies between 11 and 12, roughly 11.40. Let's visualize that between 11 and 12 on a simple number line. Using our estimate, we can rewrite the inner floor. The floor of 11.40 is 11, so our expression becomes the floor of 11 over 11. Now divide 11 by 11 to get 1. The floor of 1 is 1. Therefore, the value is 1. Quick summary. We used the floor property to move the floor to the numerator, estimated the square root of 130 between 11 and 12, took the inner floor to get 11, and simplified to 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.